Hello students, I'm Argen Kukitaev, and in this brief video we are going to discuss the multidimensional matrix manipulations that we can perform in Python. And we will talk about how to store multidimensional matrix, what are the multidimensional matrices, and which operations are available, or rather the most common operations which are available in PyTorch and NumPy packages. So let us start with simple concepts of matrix multiplication, but in particular the element-wise multiplication of matrices, which in mathematics is called Hadamard operator. So it is as simple as you have two matrices and you simply multiply them element-wise. It means the matrices should have the same dimensions generally, and for the output matrix you have the same dimension as those two input matrices, and each element is an element-wise product of these two matrices. So instead of having Hadamard product, you can think of, for instance, matrix addition. So it can be pretty much any element-wise operator here, but here I'm using the product as Hadamard operator. Now the twist which we can have in Python compared to like a typical or rather like standard mathematics is the following. Suppose your input matrix is 3 by 2, meaning it has 3 rows and 2 columns. Your left matrix, you multiply it from the right by the matrix D in this case, right? So let's rename it into D. But the matrix D only have 1 row and 2 columns and nothing else. So what are we going to do? Well, normally you shouldn't be able to multiply them element-wise. However, in Python there is this operation called broadcast, and it works not only on multiplication as usual, but also in many other operations. So you have to check the documentation on case-by-case status, because I don't remember which exactly, the whole list of operations where it works. But let's look at the result of it in multiplication. So what is the first row? It's the same as in Hadamard, right? It's like element-wise multiplication. But then look at what's going on with the row number 2 in the second row. In matrix D, which we're multiplying from the right, doesn't have the second row. So think of this like silently Python will basically take these two elements, first row, and then multiplicate, like sort of create, you know, like an implicit matrix with repeated columns, 2 3 2 3 rows, sorry, and then multiplies element-wise. So that is called broadcasting. So basically it will expand or broadcast the smaller matrix into a bigger one, right, according to, just like basically will repeat the rows. So that is called broadcast. Now I encourage you to check exactly how broadcasting work. Look it up. So I'm just letting you know that the operation is available. I'm not going to be exactly teaching you there. So let's look at a simple example of broadcasting. Where do we have broadcasting here? I believe in tensor dot, right? Let me find it quick. So I created this little, I wrote this little piece of code to just demonstrate what's going on. So I'm replicating these matrices, right? 1 2 3 and so on. So here I created matrix A and matrix B, and they're of the same dimensions, as you can see. So Hadamard product is simply a product-wise multiplication, and you can element-wise multiplication. If you just say A multiplied by B asterisk, then it's going to be Hadamard product, or element-wise multiplication. So that is easy. But now I'm showing you the example where our matrix on the right-hand side has only 2 elements. Right, only one column, one row with 2 columns, while A has 3 rows, right? So in this case, when we multiply, when we simply say multiply A by D, D will be broadcast. The first row will be replicated basically several times implicitly, as many times as it required to fill the matrix A, and the product will be computed this way, right? So that is a broadcasting which is available to you. So again, please take a look at it. It's a very neat facility, right? Simplifies coding in a lot of cases. Now let's talk about matrix multiplication, often called dot product. So the twist here is the following. If you're multiplying two-dimensional matrices, which we studied in algebra, in linear algebra, in whatever, in calculus, in school, so it's very simple. We know how to do it, right? So suppose you have two matrices, matrix A and matrix B, and if you're multiplying them, simple two-dimensional objects, right? Well, what should happen? Well, the number of columns in matrix A, number of columns, should match the number of rows of matrix B. Why? Because when we're multiplying A from the right-hand side by the B, we want second dimension of matrix A to be the same as first dimension of matrix B, right? So you see this 2 and then 2 rows. And because of that, the output dimension, the resulting matrix C, will have as many rows as matrix A and as many columns as matrix B. So when we do that, we get this result, right? So it can easily be verified by dot product. And in Python, I am showing you the examples with, let me see, tensor dot, right? I'm showing you the examples in PyTorch and NumPy in this case. So first I'm doing it in Torch, PyTorch framework. So you import Torch package, and then you will create the matrices. So in this case, how am I using creating this matrix from the Excel? Right, this one, 1, 2, 3, 4, 5, 6. I simply create a vector 1, 2, 3, 4, 5, 6, and then reshape it as two-dimensional matrix. So let's see how I do it. Right, so I create this tensor. So a range will create a list of, it will create a sequence like a vector, right? Basically a tensor with a vector 1, 2, 3, 4, 5 up until 13. It won't reach 13. It will be 1 through 12. And then I'll reshape it as 2, 3, 2 as another matrix. So I could do it as a two-dimensional matrix too. So what I'm going to show you though, is the next example. So simple multiplication is very easy. There is a function called matmul, right? Where is it? Well, there is a function called tensor dot. You can use tensor dot. If you're using NumPy, then you can use the dot operator. Where is the dot operator? Matrix. Dot in NumPy, right? In NumPy package. And in Torch is going to be called matmul. So that is for matrix multiplication. It's very simple. And nothing really surprising there. When it gets surprising is when we are multiplying multidimensional matrices, right? So single two-dimensional matrices are no big deal. Please look at refresher, matrix algebra refresher. I discussed this. So very easy. But how do we multiply multidimensional matrices? So that's where the tensors come to help us. So there is a concept of a tensor in mathematics, mathematical physics in particular. Like I studied in physics in the part where we talked about tensions and mechanics and so on. Now there are tensors in machine learning. They are called tensors, but they do not have the same properties as tensors in physics or mathematics. So they're called tensors, but really they're just multidimensional matrices. They have some features like subset, very weak subset of features from mathematics and physics tensors, but they're called tensors. So for our purpose, really, when we say tensors, forget about mathematics and physics. If you're from that background, it's not that. It's just a matrix with multiple dimensions. So how do we represent matrix with multiple dimensions? It's actually kind of hard to do it visually, right? So in this case, I'm showing the matrix A, which has dimensions 2, 3, and 2. So first dimension is 2, second dimension is 3, and third dimension is 2. So the convention in Python to print out these matrices is the following. We start from the back, right? So 2 would be the columns, right? 2 columns, and 3 would be the rows. So 3 by 2 is your matrix, right? So think of this 2 by 3 by 2. So we're showing 3 by 2 matrix first in rows. Okay, great. But then how do we show the third dimension? Well, we repeat it under. So this is what we do, right? So we show first 3 by 2 of first element and 3 by 2 of the second element of the first dimension. And we do the same thing with B matrix, and my B matrix is 2 by 2 by 2. Again, there are 2 by 2 matrices, right? Like we start from the back, right, from the tail, and we have two matrices, each one of them 2 by 2, right? So that's how we have 3 dimensions. Now, how do we multiply these matrices? Basically, there is a way to multiply them in as matrices in matrix multiplication. Unfortunately, both NumPy package and the tensor package do not do it in an intuitive way. So if you search the documentation for matrix multiplication, for instance, let's just go and search tensor, right? So we'll say tensor mmult, right? So there's a function called mmult. Where is tensor? Tensor PyTorch, right? So we'll go here, matrix multiplication, sorry, it's called. So look at this. Whenever the two matrices are multidimensional, there's this whole description. So I mean, I've been reading it and twisting my brain, and I decide I'm not going to read it. So basically, it's just too much. Like I don't understand what's going on there, and I'm never going to use it. So basically, what I'm telling you is the following. I emulated the matrix multiplication here. Where is it? Matrix multiplication of multidimensional matrices, right? So I got this one matrix, 2, 3, 2 by 2. So basically from my Excel, right? And I did it both in NumPy and then I did it in Torch. I got two different results. Neither of them are intuitive, and if anything, I would say maybe the PyTorch output is somewhat less unintuitive, but both of them are not intuitive. So I'll say this: if you have multidimensional matrices, maybe do not use matmul. So it just like it gets confusing. Like if it's two-dimensional, of course, yeah, it's very simple: dot product, matmul, whatever. But when it comes to multidimensional matrices, just start doing some funky thing. So for instance, in case of NumPy, what it does is it uses the last dimension, right? It uses the last dimension, row by row of the left matrix, but on the right matrix it uses second to last. So it doesn't use the dimension of the first dimension, but in this case it will use the second dimension. Why would it use it, and what's the help of it? I'm not sure. So I bet you can find a situation where this will work and will work fine. But yeah, I didn't find it intuitive, so I'm saying I don't think I will be using it in a regular life, let's say. But now let's look at tensor multiplication. So the tensor multiplication is much simpler. So tensor multiplication does the following thing. Here we are using Einstein notation. So I gave you the link, you can follow it and read about it. But Einstein notation is kind of easy. So when you are multiplying two matrices, you list all of their indices, and whenever the indices are repeating, you sum on them. So you see, for instance, here I'm saying index S, I, K. So I just denoted first dimension as S, second I, and third K. Now on matrix B, I denoted the first dimension as K, second J, and third as S. So K's are repeating, so I'll sum on S, on K. S's are repeating, so I'll sum on them. So I'll be summing 0 dimension and second dimension of B, and then I'll be summing the product of second dimension and first dimension of B. Okay, so we have this small matrix, and it makes sense, right? Because we are summing on the first dimension of A and then last dimension of A, and the same with B. That's why the dimension of the output should be 3, like in the middle, and 2, 3 by 2, and here it is. So how do I emulate it? Easy. We can go into tensor part of my demo, right? Tensor dot. So here I'm using the operator called tensor dot, and in tensor dot um, I'm simply listing the indices on which we are going to sum the matrices. Like, so I have matrix, or tensor rather, tensor A and tensor B. Again, I'm calling them tensor because they're multidimensional matrices, multidimensional arrays. So I'm going to be summing on index 0 of A, which is going to be the first index, and index 2 of B, right? So last index of B. And then I will be summing on index A's last index and matrix A and tensor B's first index. All right, so there will be two sums, and then I get this output, right, which I reproduced in Excel here for you. Then I'll do the same thing. Or can I do the same thing? Well, I can do the same thing in NumPy or NumPy if I'm using einsum. This is a function called einsum. It's Einstein sum, right? So what am I doing here? SIK. Remember, I named my indices in A, and I named my indices in B. So again, it means that first and last will be summed, and then there will be index on the last and the first. So please examine this Excel to understand what exactly is going on, right? So for instance, in this Excel, if I'm taking second row and second column, look what am I doing, right? So I am getting a sum. Look at this. I am getting a sum, right? First of what am I doing here? I am getting a sum of A8, it's this one, and A12, right? So I'm sort of multiplying A8 by D8 by this, and I'm multiplying A12 by E8, right? So it's like a column here in A and a row on B, but the column consists through the first dimension, not through the second dimension, right? It goes through dimension. So please examine this formula and you'll understand what's going on. It's a very simple formula actually. Okay, so that's a tensor multiplication. Again, tensor multiplication to me sounds very intuitive and easy to understand, while this matrix multiplication of multidimensional matrices is quite confusing, but I'm sure you can figure it out if you read the documentation. So that was tensor multiplication. Now, I've done already reshapes a couple of times, but reshape is a very common operator, so it's often used in conjunction with ravel. So let's see what reshape is. So in this case, I have a vector, right, which is, or matrix of one dimension, column matrix of one dimension, 1 through 12 elements, 1, 2, 3, 4. So now I can reshape it into the matrix with 3 by 2, 2 by 3 by 2. It's a 2 dimension, 3 dimension, and 2 dimension. So how does it do it? Well, the first two dimensions are this, right, from the left hand side, and then the tail 3 by 2 dimensions are the following. So how does it do it? It goes from the tail, right, of what's required. So it'll start with 2. It will be columns, right? That's why 1, 2. You see 1 and then 2. And then it goes and does the second row, 3 and 4. So it goes column by column, or rather row starting from the leftmost column to the right, that way. And then once it's done with one layer, it will go into the second layer, and so on. That's how you have 12 here. Now let's see how it looks in torch, right? So again, I create the torch range. When I say torch A range 1 through 13, it'll create a tensor, and the tensor will contain 1 through 12. You see, 1 through 12. These are integer numbers, by the way, because I didn't specify the type, and A range will create integer numbers. And then I'm going to reshape it 2, 3 by 2. How the reshape is going to happen? Say it'll take 1, 2, first row, 3, 4, second row, 5, 6, third row, right? And that was my first layer, right? Then it'll start cycling in the first dimension, right? In this dimension, right? So it'll go into the second layer, and that would be 7, 8, 9, right? So you see 7, 8, 9, 10, 11, and 12. So I saw the same example or similar example in NumPy package. So you could be using NumPy, you could be using Torch. Okay. Great. The next example is going to be probably the most interesting one of the ones which I'm showing today is a 4D flag. So, um, if you're starting to use NumPy, Tensor, or Python in machine learning, you may ask yourself a question like, why do we need, or how do we use these multidimensional matrices? Why so much attention to them? So let me show you a simple example. Let's say we want to create this data set and we probably want to work with images of flags. So in this case, I have the simplified flags, right? So the flags are 3 by 3 in my case, 3 by 3, and then they have different columns. So look at this. This is a German flag, black, red, yellowish, right? Luxembourg flag is like red, white, some bluish or light blue. Um, how can I represent these flags in computer's memory? Multiple ways, and that's the I guess the confusing part for a lot of us is there's so many ways to store the data. I'm going to show you 4 different ways right now, right? So the first way, probably the most obvious, I guess, is the following. I am going to create a multidimensional matrix which has 4 dimensions. Multidimensional array or tensor with 4 dimensions. Why 4 dimensions? Because I have countries, it's first dimension. Then I have layers of red, green, and blue. So my image in red, image in green, image in blue. And then for each of these RGBs and country, I have actual pixels, right? So that's how it works. So I have Germany and then red layer, and for that I have this little flag. But this flag is only showing me the red color of the flag. And then the second layer is going to show me only the green layer of a flag, and the blue layer is going to show me only the blues. So when I have this German flag, my first, like the top of the flag is black. That's why everything is 0. Red is 0, green is 0, and blue is 0. But then the second layer of the, not layer, but like this second sort of middle of my flag is red. And that's why you see my red is quite bright, right? It's 2 to 1. And then green and blues are both are 0. However, the yellow, how do I get yellow? Well, I get a little bit of red, well, actually quite a bit of red, and quite a bit of green. So if I mix red and green, I get this yellowish color. So that is my German flag. I represented it. So again, I represented it as a 4-dimensional array where the dimensions were country, then RGB layer, and XY. So there were 3 RGB layers, there are 4 countries, 3 RGB layers, and X and Y is 3 by 3. That's why our matrix is what? 4 by 3 by 3 by 3. 4, 3, 3, 3. Now, let me show you a quick example in Python, right? So how do I do it in Python? I believe in Python I did everything in, well, actually I did it in NumPy. So this is my NumPy array, right? Maybe I'll skip it for a second and then we'll come back. So that was one way. The other way to represent these flags is the following. What if I show country and then I show X and Y, but then my last dimension will be RGB. So I show the country, I show pixels 3 by 3, but each pixel is not just one number, it's 3 different numbers, red, green, and blue. So for some of you, this may be more intuitive, right? So I have a country and then 3 by 3 pixels of my flag. But each pixel is a long number, 3 bytes, red, green, and blue. So if we do it that way, we have to convert this matrix into the other matrix, and I did it. So how do you convert it? You're using, I would be using this method function called movedim. That's from Torch. So using Torch movedim, I can move this RGB dimension into the back. So I already have the matrix with RGB X and Y, but I want X, Y, RGB, easy, right? So I will use movedim. We'll look at this function. So you can study its parameters, but basically it can move around the dimensions. If we do something like that, we have a different sort of graph. So what's going on here? Look at this. We have a Germany, and then for the first pixel, X and Y, 0. We have red 0, right? Green 0, blue 0. But let's look at maybe the bottom of my flag. That is going to be my x2, y2, right? So I have red 255, green 204. So it's quite red, quite green. If you add them together, it becomes yellow because there's no blue. Blue is black. So that's another representation of a flag. Now I'll show you the third one. What if I don't want to, like for whatever reason, I don't have, maybe my TV is not color, it's grayscale. So I want to convert my colors into the grayscale, into shades of gray. Well, in that case, I don't need the RGB layer anymore. I need only three-dimensional matrix: country, X, and Y. Country and then pixels. So this is my matrix, right? So these are my pixels. So very dark black, and then the red is represented with some shade of gray, and then yellow with a lighter shade of gray. Now, how did I get this matrix? Well, I actually used my matrix A again, but then I summed up RGB. How did I do it? Look at this. I said torch. I used a function called sum, and then I said the dimension 1, because see, dimensions are counted as 0, 1, 2, and 3. So 0 dimension is country, 1 dimension is RGB. So I'm summing up all my RGBs, reds, greens, and blues. I'm just summing them up and dividing by 3. So basically I'm calculating like the average, and that average is my grayscale. So if, for instance, all of them, it's a white color like in Luxembourg, right? So in Luxembourg flag, in the middle I have 255, 255, 255. So in Luxembourg flag I have 255 for gray. Okay, so that was the third way. Now I'll show you the fourth way. The fourth way is used often in image processing, like in algorithms and so on, in some of them, right? Where instead of having 4 dimensions, I will have only 2-dimensional array. Well, how am I going to have it? Well, look, I have one row per country, only one row, and then my columns are, remember, similarly to this operation of reshape. Well, when I was talking about the reshape, by the way, I spoke about how to reshape from the one-dimensional to multidimensional matrix. But there is an operation called ravel. When you do ravel, it will take this multidimensional and then create one single-dimensional matrix back. So this operation called ravel. So here I'm basically doing something like ravel, right? I'm taking this 4-dimensional matrices, 3 last dimensions, RGB, X, Y, and then flattening them. So it's called ravel. It's sometimes called flattening. So this one, let's call it flattened. So instead of having some sort of a multidimensional array for each flag, now I have just flat one vector. And how did I encode it then? Now look at it, it's just one long row. But the way it works is I have the section for reds, right? Pixels, I have some section for greens and some section for blues. And within reds and reds, I have a section for first row of my flag, x0, right? And then second row of my flag, x1. And within that, I have pixels y0, each like columns, right? So basically, these are all my pixels. And for each pixel, I have red, green, and blue. So you can think of this like red part as all my pixels, but they're red component, all my pixels, they're green, and so on. Because I have my images 3 by 3, I have 9 pixels and 3 components, right? Red, green, and blue. So I have 27 columns. And you see, I have 27 columns here, 0 through 26. So this is the fourth way to represent my matrix. Now, I have this Python code for you to play with. So how would you do it? Well, what am I doing here is actually when I created my matrix, I started with this fourth representation, flattened representation, right? I took these pixels and then created them in Python here using NumPy array. And then using this NumPy array, I converted this starting with NumPy array, I converted it into a tensor. So I created my matrix D first, this one, flattened matrix D. Okay, this guy. I created that first, and then from this matrix, I created all my other matrices, A, B, and C, all 4 other representations. How am I doing them? Look, A was reshaped, so I took this flattened matrix and reshaped it. I reshaped it as 4 3 by 3, right? 4 countries, 3 RGB channels, and 3 by 3 pixels, right? And then from A, I created B. How? Remember, I said my B matrix was the same as A, except I moved my RGB towards the end. So it was my second, or rather dimension number 1, and then it became dimension number 3. So how did I do it? I used this operator called movedim of the torch framework. So my indices 1, 2, and 3 became 3, 1, and 2. What does it mean? Let's see. So my indices were RGB was 1, X was 2, and Y was 3. Instead, they became this 1, 2, and 3. I got 2. X was 2, and it came first. It became 2, and then 3. And this RGB became 1. All right, so where is my operator? My operator is here, right? 3, 1, and 2. I believe that's how it worked, right? 1, 2, and 3. I moved dimensions 1, 2, and 3 into, yeah, 1 became 3, 2 became 1, and 3 became 2. That's what I did, right? So you can see that it worked properly, like I have all these outputs here. Then just for fun of it, let's manipulate. How do we manipulate these images? So for instance, I can take this matrix B, all right, and using this matrix B, I can actually plot my flags. So how am I doing it? My matrix B is here. See, this is my matrix B, right? So I am, let me see, what are we doing here? I'm in matrix B, and then I show you two loops. There's two ways of, well, there's multiple ways, but I'll show you two ways of doing it. In one way, when I say B and then this operator, I am getting row by row of B. So I'm getting each row by row, and then I'm just showing it as an image. When I do that, it shows it as an image, as a color image here. It knows colors. Why? Because this imshow method from plot expects that my dimensions come in the following way, right? That they come in an array which is X, Y, and then RGB channels. So RGB should be at the end. I couldn't be using A for imshow function. I wouldn't be able to use A, right? So that's why I moved around my dimensions, and then I can plot my chart. Another way to do it is I create this iterator. So I know how many images. If I say length of B, it won't return me number of pixels. It will return me the length along the very first dimension of B, and very first dimension are countries. So I will be the n will be the number of countries, and then I basically go and show them one by one, and that graph is horizontal, right? So I show you two charts. One chart where they come out one after another, and in this chart I repeatedly create figure. So instead of that, in the second chart, I create figure only once, but in the figure, I create subplots horizontally, and that's how they look like. Okay. Now, to do the grayscale imaging, I showed you in Excel here how to create grayscale, right? So one way to do it was just average it's not the best way to do grayscale, by the way. There are methods which will do grayscale better, but I showed you that what I'm doing also kind of works, right? So I get the sum, but along the dimension number 1. And what is the dimension number 1 of the which matrix? Matrix C, right? Dimension number 1 of the matrix C. Where is my matrix C? I don't see my matrix C. Oh, here. My matrix C, right? I do it along dimension number 1 of matrix A. Sorry. In matrix A, my dimension number 1 is the following. The first dimension is 4, 3 by 3. Right? It's countries and then RGB channels. So I'm summing along RGB 3 RGB channels. So my matrix should be 4, 3 by 3, right? And my matrix C. And of course it is, right? So my matrix C, the shape will be 4, 3, 3. So I average it up, and then I use the same type of the loop. I print with image show, but this time I say my color map is gray. And when I say gray, it will expect a two-dimensional matrix, right? Because it knows that for two-dimensional matrix there will be only one number in the output. And wait a second, why is it not showing it as a gray? Because I'm not getting it from C, right? Okay, now it's gray, right? So I'm cycling through the matrix C, which is grayscale, because there's only one number, luminosity, and I'm interpreting as a grayscale. Okay, so that was that. The other thing I wanted to mention was collapsing the dimensions. You remember how I said that when I'm summing on one of the dimensions, let's see, where is my collapsing? Collapsing and adding dimension, right? So think of this. If I have a matrix A, and then I look at all the elements, if I write this A and then colon 1, right? So it's going to take all the elements starting from 0 but not reaching 1. And that's only one element. So you would expect that because this matrix had 4 dimensions, 4, 3, 3, 3, you would expect to get the matrix only with dimension 3 by 3 by 3, because from the first dimension we're getting only one number. However, when I get this, when I print this, I see that this is a tensor with, in fact, 4 dimensions. It's 3 by 3 by 3, but first dimension has only one, size 1, right? So if I do it this way. However, you think of if I get the matrix and I get only the first element, it should produce the same result as A1, and it kind of does, right? So if I just do A0, then its shape, though, is just 3, 3 by 3. It's only 3-dimensional. It's not 4-dimensional. The tensor seems to be the same, almost exactly the same, if you compare these two tensors. The only difference is that this when I pull it this way, because this way it knows that I'm trying to get a slice of my matrix, so it will preserve the first dimension. Okay, it will have only one element there, but it will preserve the dimension, and that's why there's 4 dimensions there. While in this operator, I get kind of the same result, but the first dimension is dropped, so it's collapsed. And instead of having 4 dimensions, this tensor has 3 dimensions. Now, once I got this A0 with 3 dimensions, I can add back another dimension by adding none. So if I add none in the beginning of this matrix, what will happen is, look, it added back this 1 dimension, and now my tensor is equivalent to the tensor in my first example, first row. So please examine these this little example, because it may save you from a lot of trouble. In the similar similar idea is both in happens also in NumPy too, not only in tensor. In torch framework. In any kind of multidimensional framework, there is this case where you either collapse the dimension, let's say you sum across one dimension, and then it just disappears, or when you need to add back the dimension. Like oftentimes you're running a function and it will say, well, you don't have enough dimensions, so you may need to add the dimension, and this is one way of doing it. In this case, this was in torch, right? So you can do the same thing in NumPy, of course. So that was my 4D flags example. I believe I went through the whole thing. Right, so these are different ways of using images. So in machine learning class, we will be using some of these representations, at least 2 of them, if not 3. Right, so just exercise and learn how to convert from one dimension to another, or at least understand that it is possible, that these operations, and then when you run into the necessity, you can always look up these operators in the documentation.